The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
We have the opportunity today to listen to Dr. Jason Weiss from the University of Purdue to present some research along this. This is one of the common questions that we run into when we talk about this subject is what is actually the research. If you would, please.
Well, thank you very much. And before we jump too far into this, what I'd really like to do is to take a second and acknowledge a lot of the work that we're going to see is done by several different students. Tim Barrett, Hungfeng Sun. We've been fortunate on this to work with Laurent Barcelo as well. And I want to just point out that that's a lot of people go into making some of the data that we see here. It's a nice one little chart, but it's taken someone a year or 2 years to put that chart together. What I want to really do now is talk a little bit about the motivation, talk about the who, what, when, why, how of Portland-Limestone cement, and then I really want to jump into discussion on shrinkage because this has come up at several of the different talks. I think there was a lot of information before presented in Toronto, and I think Paul did a very nice job talking about some of the other properties. So today I really want to focus in on shrinkage after we get through sort of the basic motivational questions. As Paul mentioned, Portland-Limestone cement is now currently in the cement specifications, ASTM C595 and AASHTO M240. Here's a picture of a typical Portland-Limestone cement. When you look at it in the microscope, all the particles are not different colors like this. That's been added afterwards. But it gives you a little bit of an idea of what the picture is that's going on. Basically, the white particles here are our typical clinker portion of the cement, and the yellowish particles are the limestone in this case. And Paul covered quite a bit on the background, but we're looking at really 5 to 15% additions. And one of the things that I will keep coming back to when we talk about PLCs, we're really talking about interground materials. I will give a 1 slide or 2 slides on materials where limestones have been added that's a little bit different than the interground materials. But what we're really focused on here is interground limestone as part of the production process. The next question really, now that we know a little bit about what it is that we're talking about, is why do we want it? And the real reason that we want this is really looking at the sustainability issues associated with cement production. You hear people talk about numbers that are high as 7 or 8%. Here you see a pie chart where the numbers are about 5%. 5 to 8% of the world's CO2 production comes from the cement and concrete industry. And you may say, wow, that's a really high number. Cement must be awful. Well, one thing that we have to remember is concrete itself has a relatively low carbon emission, but the fact is we use an enormous amount of it. We use a lot more than we use any other material, and even though we have a low carbon emission, we're looking at ways to make this better because if we can reduce this number, that's good for everything. About 50% of that CO2 that's coming is coming from the calcination process, 40% is coming from the combustion process, and 10% coming from transportation. If we can replace some of that clinker, we can really act to reduce some of the CO2 coming from calcination, some of the CO2 coming from combustion, and substantially reduce the CO2 that's being produced with that concrete. So really the real big takeaway on why we want it is, again, the sustainability issue. So I would say there are three main areas that we can focus in on. We can reduce the cement contents in our mixtures, and I think that this is a good thing not only from a sustainability issue, but there's cost benefits, there's durability benefits in doing that. We want to make our concrete structures last as long as possible, but what we're really looking at in this particular talk is the ability to reduce the clinker and get the same performance. And if you can reduce the amount of clinker, reduce the amount of CO2, and get a similar performance, it seems like something that we should at least be investigating. The question is who and who has done research on this, and I know one of the topics that comes up almost each time we would talk about this is, wow, this is something that's new and radical and it's out there. Has anybody ever looked at this before? There are over 1,000 papers on Portland limestone cement. One of the nice things that's happened is there have been several review sessions where people have gone through and essentially assembled these, and I believe, if I'm not wrong, all of these documents are free of charge, where they've taken all the information, they've put it together. You can download this information, you can contact any of the authors and get this, but I think they all do a fairly good job of summarizing what's out in the literature and what the rest of the world has experienced with Portland limestone cements. One that I will slow down a little bit to talk a little bit about is really the how, and I think the how is important here because this differs from what we see in a lot of different applications. In the North American experience, the real thing that I will keep coming back to is we're targeting similar performance to the OPC. So one of the things that we're gonna keep coming back to is we're using less clinker. By using less clinker, we have less clinker in the system, so we're diluting the clinker a little bit, and typically what we're gonna see is the cement is ground finer. So in general, Portland limestone cement is going to be ground finer than the OPC. One of the reasons for this is to overcome dilution. So if you look at a normal strength development curve for our OPC, if we deal with our PLC, we're grinding it a little bit finer. We're going to see more rapid strength development initially, and then we're going to see that rate of strength gain slow down a little bit. But this is mainly influenced by the fineness of the material. The higher fineness helps us because it can act like as a nucleating agent, as Paul mentioned. It also helps us because it can improve particle packing. The other thing I will mention is, and there'll be a talk on this that we'll be doing tomorrow, but PLCs show substantial benefits when you start using them with other supplementary materials. And we'll talk a little bit about that today with slag. Tomorrow we'll talk extensively on that with fly ash, where you can see substantial benefits. So even though we typically say similar performance, there are times where that performance can be greatly improved. So a couple of things we'll talk about are really what are the potential consequences of using the Portland limestone cement. And this is where I'm going to skip this slide because I think Paul did a great job talking about the reduced porosity and increased strength. But I really want to get in on this discussion of fineness and shrinkage. And one of the things that I really want to talk about here is there are a lot of reports that say finer cements crack at earlier ages. And I'm not going to dispute with a lot of those authors because we've authored a lot of those papers. Okay, and this is something that you can see if you go about this with the conventional OPC types of mixtures. The Blaine fineness is often used in this study, and that's often the single measure that we've got. And I think one of the things that is going to become really evident as we look at this is Blaine fineness gives us a number, but may not give us the complete picture of what's happening in terms of how these materials behave. So here's a typical OPC that's ground finer, and we see the age of cracking moves from 2 days, or from 4 days up to about 2 days. But again, remember, that's a conventional OPC system where all that's been done is the clinker is ground more and more fine. And I think we need to get into this a little bit more to understand what's going on with Portland limestone cements. And I think before we get into lots of data, one of the things I want to point out is Thomas Young, the Marquis de Laplace. Basically, one of the equations we're going to keep coming back to is what's known as the Young-Laplace equation. And really the idea here is we can relate the stresses that develop inside of the capillary fluid to the surface tension of the fluid, a contact angle, and the size of the pores that start coming up inside of the system. So we're going to keep coming back to this idea because what I'm going to talk about is really fundamentally rooted in this equation right here, where if we understand the pore size distribution and we understand how we're modifying the pores and what size pores we're modifying, we can get a direct implication on what we're doing to the shrinkage of the system. Right, so again, to take Young-Laplace to a slightly different level, most of us will probably remember it was second or third grade where we got 2 glass slides and we got the opportunity to run over to a microscope and we put a bug or something nice and disgusting in there and we looked at it under the microscope, and then you tried to pull those 2 glass slides apart and it was virtually impossible. All right, especially if you had a drop of water in between those 2 slides, it's really impossible. You've got 2 silica-based sheets where there's water in between them. High surface tension holds those 2 layers together. That's the same thing we have going on inside of the pores, inside of our system, and this is really what is going to drive the shrinkage. Again, same equation that we looked at before. The stress is related to the surface tension divided by the pore sizes inside the material, and we will keep coming back to some general plots, but here you can see the idea. The stresses are relatively low with big pores, and the stresses get much, much higher as you get to smaller pore sizes. All right, so Shrinkage is really related to the size of the pores that's emptying, all right? Pores smaller than a few nanometers, we worry about other things. Pores bigger than about 50 nanometers, there's really not small enough that we start to generate significant stresses. So we're going to focus in on this region right in here. From about 3 nanometers up to somewhere around 20 nanometers is really the range that we're interested in for most of the shrinkage that we're going to be talking about. Right, now I want to point this out really quickly here, and I'm going to ask you to sort of remember this particle size distribution curve. Here you can see a particle size distribution curve, and this is for conventional Portland cements. And this was out of one of the studies I mentioned that said finer cements are more prone to crack. But what I want to point out is as the fineness has been changed, you see these curves shift pretty substantially over toward the left-hand side of the screen, and the whole curve slides relatively uniformly. I think we're going to contrast this, or I'm going to try to contrast this with what we see in the PLC systems to show you that we really are going to get a different particle size distribution, and as a result of that, we're going to get a different pore size distribution inside of the material. So now I'm going to talk about a couple different systems, and I will go through really what's been probably a 5 or 6 year study going on into this, and we're going to talk about different clinkers. We've got up to about 7 or 8 different clinkers that have been looked at from different commercial plants that I'm going to try to combine into here. We're going to talk about these in terms of different phases, but this was not a well-orchestrated 18-phase project when we started. This is, we'll test this particular cement, we'll test this particular cement. Now we're going to go back and look at some of the similarities that we've seen in some of this information. So one of the first ones that we looked at, this is a commercially ground blended cement. Again, it's a Portland-Limestone cement, so it's been in a ground, looking at 0, 5, and 10% limestone additions. And essentially what we're going to look at here is the red line is 0% limestone, the blue line is 5%, the green line is essentially the effect of dilution, and the black line here is 10% limestone. And what we can notice if we look at the autogenous shrinkage here is we've got very similar shrinkage. All right, no additional shrinkage coming from the underground limestone, even though we see the Blaine fineness has gone from 382 up to 461. So even though it's finer, we're not seeing additional shrinkage in that system. Right. In addition to this, we've used a ring test, and I will come back to this a little bit later on. The ring test is not to just to quantify the length change, but it's to quantify the cracking potential of the material. So the idea is we cast a concrete mortar or concrete around the steel ring. The concrete wants to shrink and get smaller. The steel prevents that from happening. We can measure the strains that develop inside of the ring. We can use those strains to calculate what the pressure had to be on the ring to get that, and we can turn that around and say this is what the pressure and stresses are inside of the concrete, and this gives us a very quantitative way to talk about the stress development inside of these different concretes. And one of the things that we can look at when we start to look at these different PLC mixtures, and we see a lot of different lines down here, the blue are the plain system, the red is 5% limestone, the green is 10% limestone, age of cracking shown here. Again, finer cement, we don't see an increase in the cracking potential, we don't see an increase in the strain or the stresses that are developing inside of the system. One of the other things that we did while we did this particular study is we actually looked at the long-term shrinkage of these samples. So we took samples here that are about the size of a piece of chalk, about 4 inches long, about 10 millimeters in diameter. We put them in a CO2 purged environment. We left them sit there for about 180 days to get the full shrinkage out of these pastes. And what you can see again, 0%, 5%, 10% limestone, the results all lie up on top of each other within the statistical variability that you would expect in this system. So again, the main point that I want to drive home is even though we have different Blaine fineness numbers, about 80 points finer for the 10% limestone system, we see identical shrinkage over a really wide range of relative humidities that we'd be looking at here. Now in the second study, and I want to point this out just to clarify some of the differences because I think it becomes easy for people to get confused when they look at different papers. I want to point out that we did another study where instead of intergrinding the limestone, we added the limestone. And one of the things that I want to point out is we're going to talk about small, medium, and large limestone particles, 3, 17, and 100 micron. I want to point out one thing that's very different than every other system I'm going to talk about this morning. These are not equivalent or similar performance systems. Right? When we start replacing 15% cement with 100 100 micron limestone particles, we will notice a decrease in the strength. So they're not similar like we were talking about before. But again, when we use the relatively fine limestone, we see a similar trend to the stresses that are developing. As we go to bigger limestone particles, again, where we're reducing the strength and we're reducing some of the performance, we see lower stresses developing in the system. I want to point this out because this is a different system than we've talked about with the PLC systems, because they're not equivalent cements and they're not interground cements. Third phase of this is, again, just to look at a different binder. And again, I want to point this out because this is a different binder, 0.38 water to cement ratio. Sealed shrinkage up here. The green and light green lines, and I don't know why we did green and light green. I guess that was to stay green with the theme. But these are the drying. This is drying down here. These are the sealed shrinkages, and you're hard-pressed to see a difference between those lines. And if you move over here to the stresses that are developing in the system, again, you see maybe a slightly higher stress in the OPC, but they're relatively similar for the sake of what we're discussing. So I really now want to get into a little bit more of the final study that we've looked at here, where we're going to get into a little more detail. We're going to look at the shrinkage and cracking potential in 3 systems. It's going to be the clinker with the limestone interground. And again, all the interground things that I'm discussing here are interground commercially, which has a lot different technology than if you're intergrinding these in a ball mill inside your lab. We're going to do a 0.39 and a 0.34 mixture, and for times I'm only going to show the 0.34 mixture with 55% by volume by sand. Here we've got an OPC which has about 3% limestone, a PLC which is 11% limestone, and a PLC slag system which is 10% limestone and 12% interground slag. Again, I just want to point these pictures out here very quickly. One of the things that's interesting to note is if you look at the OPC system, you see a lot of very large particles. And as you start to go to the PLC and the PLC slag particle systems, some of those big particles will disappear. You'll see a lot finer particles. Most of these finer particles are the yellow particles, which are the limestone. And then you also see some of the slag particles interdispersed, as we see over here. All right, so to talk a little bit about this, I want to show particle size distribution, talk about reactivity, talk a little bit about shrinkage, and then the cracking potential. So the particle size distribution, again, I want to compare and contrast this to what you saw maybe 10 slides ago. All right, and I pointed out when we looked at those particle size distributions, we said in a conventional system, if you change the blade fineness, that curve sort of marches over to the left as it gets finer. Here you can see that there's a slight shift to the left, but we don't see that sort of parallel shift. And what you notice if you look at the frequency distribution or the derivative of this curve, you see essentially what we're doing is we're losing a lot of these big particles, these 30 micron, 40 micron, 50 micron size particles, and we're replacing them with some of these smaller particles in the 2, 3, 4 micron range, and those are really that ground limestone. So what we're doing is we're getting rid of, on a microstructural level, the basketball size particles. All right, we're getting a lot of softball size particles, and we're ending up with a few ping pong ball size limestone particles in the system. Right. Now, the proof is really in the pudding in this, is in what size pores you get back out of the system. And what we've done here is we've done a test where essentially we've dried out different pastes, and by drying them at a known humidity, you can determine the relative proportion of pores inside of that humidity range. And if you look at the OPC, the PLC, and the PLC slag here, all right, from the highest humidity way down in here to about that 60% humidity I was talking about before, that 3 nanometer pore size range, you would say that these curves are virtually identical. We see a slight increase or a slight difference here with the PLC and the PLC slag systems, and those would be at about 55% relative humidity, where you might see a slight increase in the volume of the pores. But in general, these pore size distributions are very, very similar, even though the blade fineness numbers are very different in those cases. So the chemical shrinkage, to really talk a little bit about this, chemical shrinkage is just a volume reduction that's associated with reaction. You start out with 1 volume of cement, 1 volume of water, and you end up with something like 1.86 total volumes when the whole system reacts. This has been observed and this has been around for a long time, but what I want to do is I want to just point out here that if we look at the chemical shrinkage by binder, this is by clinker and ground limestone, one of the things that we'll notice is we see very similar amounts of chemical shrinkage, very similar amounts of reactivity during the first week, and then we see the OPC maybe slightly higher again. The reason that this is similar, even though the system has been slightly diluted, is because we've got a more finely ground material in the system. The PLC system is more finely ground. Again, we see the slag system is a little bit slower due to the slag, but it starts to catch up as we get out toward 28 days. The autogenous shrinkage of this system, again, autogenous shrinkage is simply the shrinkage of a closed system that's not losing moisture to the outside, right, not subjected to temperature change. Right, if we look at this shrinkage from the time of setting, what we'll notice here is the black line, again, is the OPC, blue is the Portland limestone cement, brown is Portland limestone cement with slag. Out to 3 weeks, I believe is what we see on this curve, 2 to 3 weeks. We see very similar shrinkage with the slag being slightly slower, as we would expect because the slag is slightly slower to react. If we look at this in terms of restrained shrinkage and cracking potential, right, again, similar trend starts to emerge where we say OPC, PLC, PLC slag, and I would argue that it's very difficult to determine anything from this curve other than they really look similar. All right, and if somebody wants to get in here and talk about this one cracked an hour ahead of the other one, I'm going to tell you that the variation of that test is more than a couple hours that we're looking at here. So again, the takeaway from this slide is they're very similar systems. So if we want to get into some of the main conclusions of the last part of this, particle size and particle size distribution, the big thing we see in the PLC and the PLC slag systems as compared to the OPC system is really less big particles and more of the small particles being the ground limestone. It's really the ground limestone that's the fine particles. The pore size, though, as it relates to shrinkage is very, very similar in these mixtures, all right, which means that we're going to have similar shrinkage, and I think we've shown that. We see slightly less early age chemical shrinkage in the slag system, but the other systems we see being very similar, mainly due to the finer grind. We see slightly lower shrinkage for the PLC slag system, very similar for the PLC and OPC, and again for the OPC, PLC, and PLCS, very similar restrained shrinkage in the overall takeaway. So again, the summary of the overall observations that we can make here, PLC is really not just the dilution of the OPC. It's not really taking 15% out of the clinker away and hoping for the best. It's really a system that's engineered to have finer particle sizes to increase the reactivity of those systems and give you a very similar pore size distribution. And because of this, we tend to see we have a lot of similar properties, similar strength, similar modulus, similar transport properties, similar shrinkage. It's not surprising because we've got a very similar pore size distribution in those that's really been engineered. The PLC, as I mentioned, the PLC and the PLC slag systems are engineered differently to obtain similar performance. Again, more fine grinding to get that similar performance. We've shown similar or less autogenous shrinkage with the PLC and the PLC slag systems, and this means that we have similar or less shrinkage cracking. And I believe all of these observations, in addition to being experiments that have been performed, can really be explained by what we've seen with the Young-Laplace equation and the very similar pore size distribution. So with that, I'll turn it back over to our speakers if there's...
Are there any questions, Mason?
I'm wondering, for one of the systems, we did the shrinkage test in nitrogen environment. Is this particular system more susceptible to carbonation or is carbonation?
The reason that the systems are done with nitrogen purge is if you take a small paste system and you expose it to carbon dioxide, you're going to get carbonation shrinkage in addition to the water-based shrinkages that we're seeing. So it's fairly common when you do the small samples like that, because they're sitting for so long, that you do them in a nitrogen purge. And a lot of the older literature that you'll look at does them in a nitrogen purge.
So if you were grinding these things in the lab with the ball mill, what kind of differences would you get compared to the industrial process?
Yeah, so I mean, this is a trickier question. You know, when you're using a ball mill in the lab or you're using a jet mill or something like that in the lab to grind these. What I want to say is it's a slightly different process, because you will see that the limestone grinds finer than everything else because it's softer, right? So it's not a huge surprise that a softer material is going to grind more finely. But I believe when you get into the grinding plus the separator technologies and different things like that, when you get to a commercial scale, it's a very different system than what you would see in a just allowing balls to drop on them in a simple ball mill that you have in the lab. So I think that's one of the things we've got to keep in mind when we look at these. We're getting to that higher blane fineness in a slightly different way than just grinding it finer and finer and finer. And this is why it differs a little bit from the OPC system. So I don't know if that fully answers the question, but I'd be happy to share data we have from the lab and discuss it with you. Thank you. Thank you.